Test.
Oh, there we go. Okay. Great. Okay. Yeah, great. Hello, crypto.
Okay.
Good morning.
Give me a second. I'll just give you the introduction.
Yes, go.
All right, perfect. So the next talk will be actually a joint talk for two different talks. The first one is R-V-SIS, Succinct Linear Function Commitments from Lattices by Ben Fish, Xu Lu, and Sai Vaseli. And Sai will give the talk. And right after, we'll have lattice-based succinct arguments from vanishing polynomial by Valerio Cini, Russell Lai, and Julia Malavolta. And Valerio will give the second half of the talk. So Sai, please go ahead.
Yeah. So as stated, this will be a joint talk. We'll be talking about some different things, and our papers are separate, but we have a soft merge talk that we're both taking half of. So yeah, my name is Sai Vaseli. I use they, them pronouns. This is joint work again with Ben Fish, Xu Lu. We're all at Yale. And we are going to be talking about succinct linear functional commitments from lattices. This clicker doesn't seem to be working. Oh, okay. Okay. So anyway, okay, start with our results. The main part is that we get lattice arguments with O log n, log n verifier complexity. We have an asterisk here to be, I feel like, more honest, because this relies on a galactic algorithm, which is only concretely efficient at instance sizes that are completely impractical. So in reality, we use like something like Karatsuba for this, and then we get something like O log to the 1.58n verifier complexity. Then we have log size proofs. And so we make constructions for both cyclotomic rings mod Q and also integers mod Q of linear map functional commitments and inner product arguments, polynomial commitments, and a snark for R-V-SIS. This is not all in the conference version, but it will be in the ePrint version, which will be out any day now. We will have the same title. And all of these are extractable, pre-processing, and structure preserving, except for the norm bound checks that we have to do, but you can linearize those using various techniques. And in particular, in this talk, I'm just going to be talking about the linear map functional commitments. So we're going to start with this abstract equation. This form has been used in previous works like Groth 10, LRY 16, and Atem Grimmer 20. And basically, we have the function, which is these FIs, the function vector, and the witness vector, which is these XIs. We want to compute this inner product, this linear map on the witness. And we see that if we express these as these two polynomials on the left-hand side, that in the negative and positive powers of this variable y, we end up with the evaluation being the constant term, and then all these cross terms, which are the bi with the powers of y for I not equal to 0. Okay, so we're gonna see how we situate this in the lattice setting using these translation techniques that were developed in previous work here last year, which is ACLMT 2022. And so the first thing we need to do to put this in the lattice setting is that we're going to need f and x to be short relative to q. And then we're going to start by turning these two into commitments. So this black commitment means that the verifier is already going to have this, whereas the magenta color is going to signify things that the prover is going to provide. Either way, both of these are going to be computed basically the same way. One will be done like pre-processed for the verifier, the other one the prover commits. But they're both going to use this thing called the what we're calling ring Vandermonde SIS commitment. They give a different name for the same commitment and are going to show a different construction using it in the next talk. But either way, basically you take that polynomial in the y and you plug in like a concrete randomly chosen value from the ring. And then you just compute the commitment like this. And we see that this is basically like a AdgeTie SIS commitment, except that we are using a Vandermonde key. And this is similar to assumption used in passline in some related works. If you replace sampling V from the ring and instead pick it from the primitive roots of unity, then you can reduce binding to this Vandermonde SIS assumption that has been studied in other works. Okay, so this is how we compute our commitments. Again, we have that the commitment to the function is preprocessed. The Y is the claimed evaluation the prover will send. And then instead of sending this cross-term polynomial on the right, basically we send a short preimage for it, and that will be the proof that the prover provides. And we're going to show how with a trapdoor matrix, we can give these sort of short preimages for the powers of Y, where we take a linear combination of them in order to get this. The prover key basically consists of these short preimages UI for all the powers that are not that constant term of the Y0. And we use a trapdoor public SIS matrix A. These were introduced in Chancho and Picart 12. And so when we have these, the prover just computes the proof like this, where they use those cross-term BIs that we had labeled to take a short linear combination of these short preimages to compute pi. And then when we sort of plug this in based on what we know about the UI, just by linearity, we get that those should be, instead of V sub I, V to the I, but we get the correct sort of cross term on the right there. And then, so we've said that F and X need to be short. And if this is true, then the BI will be short. The UI are short because we've generated them during our trusted setup with our trapdoor for the public SIS matrix A. And then all this leads to pi being short. And so evaluation binding means that for a given function and witness that we can't open to two values y and y prime. But let's say, of course, that we do. Then we need to be able to break some assumption. And so if we had two accepting verifier equations like this, we could subtract them from each other, and then we end up with this equation on the bottom here. And so the assumption it's going to break is an assumption within the crisis family of assumptions that was introduced in ACLMT 22. And the assumption, we're not going to give the formal version, but the spirit of it is basically that you can only generate short preimages for targets within a short linear span of the VI, the things you're given preimages for, or for random targets, because of course we can just pick a short preimage, multiply by A and see where it lands. And so the idea here is that Y prime minus Y is going to be short because we are enforcing norm bounds on the Y, while for V picked at random and all the VI, there's some other things we need to select right to make sure this happens, but they will be long with high probability, as will random targets that we end up hitting if we just sample a random preimage. And so we basically are seeing that it's hard to find a short preimage for a short target. Okay, so we're going to extend this to multiple outputs next. So let's say that instead of just wanting to evaluate one function, we want to evaluate several on the same committed witness X. So, we use a pretty standard technique of just taking linear combinations, and we can make this aggregate proof. But of course, the set that we pick these challenges HI from, we need to be a little bit careful with, especially in the lattice setting. We're able to do something here, which I think is interesting and interesting observation, works out really well for us, which is that in terms of extractability, we're not going to show it here, but the prover will be submitting a separate knowledge proof with choosing our knowledge assumption we're able to extract X. And then it's unnecessary to extract the sort of hypothetical pi I that you'd have for sort of each individual evaluation proof that would be inside pi. And without needing to do this extraction, we have more flexibility in the challenge sets and can you pick something more efficient than what's required by a lot of previous works where you would have to extract these because you'd maybe be getting the witness from the pi i's, where we are not. We're getting it from a separate proof. So let's just say we get this extracted X from this other proof. We plug it in. We end up with this as our new equation. And we see that this term, the first summand in the HI needs to be 0 basically by our crisis assumption because it is the constant term. And we can only have a pi is equal to something that's in those power of yi's, where I is not equal to 0. And so we're going to call this a polynomial in a multivariate polynomial P in the HI. And so we want basically this sort of Schwarzschild-like property, except more general, because we're working over rings. For sampling the random HI, we want this to evaluate to 0 only with negligible probability if P is not the 0 polynomial. So this will mean if P is a 0 polynomial, we know that all the evaluations were correct. And so the nice thing we can do here is we can pick an exponential size exceptional set. Exceptional set is this set where the pairwise differences between distinct elements are invertible. But we only need them to be invertible over RQ instead of R, as many previous works need. And this is actually possible to pick exponential size exceptional sets over RQ, whereas over R instead of RQ, there's a lot of evidence showing that they don't exist basically, and you need to do repetition because you can't find it. You can only find polynomial size sets. However, we can do this with large Q, and then we can invoke something called generalized Laurent-Ferretti theorem. It's sort of like a generalized Schwarzschild for rings. And then finally, we find that even for a single function, that it's better to decompose both the witness into a ternary witness and commit to that, and the function into a log number of ternary functions, and then use this batching to compute an aggregate proof. And this is just a more efficient way to even prove a single function. So I will just wrap up with some proof in SRS sizes. This is at the 128-bit classical security level. And so we have fairly high constants, but especially for larger proof sizes. This is, by the way, for the ring Z2 to the 32. We don't need to use like bigger fields like an elliptic curve world for security. So we just pick what's actually like good for the circuit we want to talk about. Yeah, so the proof sizes end up being more competitive, definitely on the higher side, because we have small growth but high constants compared to other post-quantum works, at least. We have at least a really small verifier key. The prover key is pretty good until we get, again, to these really big 2 to the 30 instances, and then small commitments again. And also the other thing is that these are maximum proof sizes. So when F or X are sparse, which is common in a lot of practical applications, or when they have norms that are much smaller than the bounds than 2 to the 32, that's actually reflected by the proof size. So again, these are just bounds on the proof size. And if we just need binding, like if the commitment's created by a trusted party, we can reduce the proof size by 65% and the prover key size by 75%. And sort of looking over different norm bounds and instance sizes, the smallest witness compressing proofs start around 165 kb for binding, and 668 if you also want extractability. So because of things we have non-interactivity, pre-processing, structure preserving besides the norm bounds. There's a lot of properties that make this good for recursion, and we sketch out different ways you might be able to do this, but don't give a full construction, and this might give some hint of the sort of lower bound of the recursion threshold for this. Yeah, so I'm going to go ahead and give it over to Valerio now. Down is the next slide. Yeah. Okay. Good luck.
Hi, so my name is Valerio. I will be presenting joint work with Russell Lai and Giulio Malavolta, named lattice-based succinct arguments from vanishing polynomial. So as the title suggests, we work on constructing succinct arguments from lattices. And if we look at the literature, there have been mainly 3 different approaches to construct such succinct arguments, each with its own drawbacks. So if we classify the different construction depending on if whether they are publicly verifiable, have efficient verifier or efficient prover, we see that none of them satisfies all these 3 characteristics at the same time. And mainly if we focus on a proof system which are publicly verifiable, we see there have been 2 main kind of construction. One based on this bulletproof style folding, which gives you a publicly verifiable linear time prover system, but where the verifier is also linear in the size of the statement that you want to prove. Whereas recent construction from last year by Albrecht et al. That also Psy mentioned, gives you a publicly verifiable proof system with a sublinear verifier, but where the prover grows at least quadratically in the size of the statement that you want to prove. So in this work, using this power vanishes things assumption that Psy were saying about before, we achieve all these 3 properties at the same time. And I should mention that there is also like a concurrent work by Bootle, Chiesa, and Sotiraki that also achieves the same properties. So our result is as follows. So we introduce this vanishing SIS assumption, as we call it, and that can be seen as a generalization of the SIS problem. And we noticed that this assumption gives directly a construction of a commitment scheme with a bunch of nice properties. So first of all, the commitment key is polylogarithmic in the size of the witness that you want to commit to. It is additively and multiplicatively homomorphic. And these 2 properties allow us to construct an efficient argument system for proving opening of such commitments. And with this toolbox, then we will be able to construct a new lattice-based succinct argument for MP with the properties that we were saying. So in this talk, I will not present the lattice-based succinct argument for MP. You can find that in our work, which will be soon on print. But I will mainly discuss the idea that allow you to construct such a proof system. So the results is the following. So we have 2 different instantiations of this proof system. One based on folded technique, and the second based on this knowledge assumption from Albrecht et al. From last year. They both have polylogarithmic proof size, quasi-linear time prover, and polylogarithmic verifier runtime. The folding instantiation as a transparent setup that can be made non-interactive using the round oracle. The second instantiation using this knowledge assumption is naturally non-interactive, but as a trusted setup and requires this knowledge assumption. Okay, so now let's move to the main idea, and let's introduce first this vanishing SIS assumption. So the standard SIS assumption is the following. So you're given a matrix A wide, and you're asked to come up with a short preimage of 0. So a vector U such that AU is short, and AU is short, and AU is 0 mod Q. And how can we generalize this one? So this is just restating the assumption. So the problem can be restated in the following way. So if you see the vector U as the coefficient of a linear function, what what the problem is asking you is to find a short linear function, so a linear function with short coefficients, such that it vanishes all the given point, where the point are the rows of the matrix A. And then naturally one could generalize this assumption by asking the adversary to come up not with just a linear function, but with a polynomial that vanishes at these given points. And this is exactly what the vanishing SIS assumption asks you to find. So like one concrete example, in the case of like a univariate polynomial. So the assumption will be the following. So you're given a point B in some ring RQ, and then you ask to find a short polynomial that vanishes at B. And this can be rewritten as finding a vector P in R to the M, such that this matrix times P is equal to 0 mod Q, and P is short. So it can be seen as like a SIS problem, where the SIS matrix is not uniform random anymore, but it has some structure. And we will use this structure to produce an efficient proof system for such a commitment scheme. Okay, so the commitment scheme is very natural. So if you want to commit to some polynomial and you're given some random point V, you just evaluate this polynomial at the random point that you're given. And this is the commitment to the polynomial. The binding property follows directly from this vanishing SIS assumption. So namely, if you are able to find two different polynomials that have the same evaluation at this point V, then you also find the difference is also a short polynomial that vanishes at B. And since we are now working with polynomials, we see that we have two nice homomorphic properties. So first of all, it is additively homomorphic. So if you sum the commitment of two different polynomials, then you get the commitment to the sum of the polynomials. And also this also works for the multiplication. So if you multiply the commitment of two different polynomials, you get the commitment to the product. So more concretely, let's say we have two vectors, A and B, and we think of them as defining some polynomial P hat and P, where by P hat I mean that you evaluate the polynomial at the negative powers. Then when you multiply these two polynomials, you get a polynomial that is defined by the vector given by the convolution of these two vectors. And as I was saying before, in the constant term gives you the inner product between A and B. And now here the catch is that the convolution polynomial P hat has a linear number of terms in the number of terms of A and B. So you don't get a quadratic blow up, but you just get a factor 2 blow up in the size of the new witness. Okay, so let's move to the key idea. So we want to be able to prove some quadratic relation using this new commitment scheme. And let's say the most simple quadratic relation that we want to deal with is proving that some vector x is binary. So you want to prove that each of the entry of x is either 0 or 1. And the way you're going to do it is by committing to, so the prover is going to commit to x using this like primal basis commitment with the positive powers and with the negative powers as well as constructing the commitment to the O1 vector. Now, using the homomorphic properties of this commitment scheme, you can get a polynomial where the constant term is the inner product between x and x minus 1. So proving that x is binary would be equivalent to proving that each of these summands in the constant term is equal to 0. So if we get a proof system for such a thing, then we will be able to prove that x is binary. So as is stated now, it's not proving that the constant term is 0 will not give you that x is binary, because the sum could be 0, but not each of the term. So what we are going to do is, as Sai was saying before, we will introduce a short linear combination of this term that will allow you to prove that this is 0. So in particular, we will add to the CRS, or to the public parameter, some SIS instance age. And then by committing to h other mod x instead of x, what you will get in the constant term of this polynomial is the inner product between h and x other mod x minus 1. So if you're able to prove that the constant term is 0 by relying on the hardness of SIS, you prove that each of the summands is 0 as well. Okay, so to get a proof system for this quadratic relation, what you're able to prove, what you want to support is a language of this form. So you want to be able to prove that the commitment Cx and C bar X have the same witness X, and also that you know a W with a constant term 0, so there is no V to the 0 in the left-hand side of the second equation. That satisfies this equation. And we will construct such a proof system using either the crisis assumption from Albrecht et al. From last year, or bulletproof style folding techniques. So let's see the first construction. So to just briefly recap what the knowledge crisis assumption says, is very briefly, like in the public parameters, you're given some matrix A and T, and a bunch of tuples UGB, such that A times UGB is equal to T times GB. And the adversary is asked to come up with a new tuple UC that satisfies the same equation. And the assumption says that the only way an algorithm can do that is by computing a short linear combination of the given preimages. And given this assumption, a very simple proof system is the following. So in the public parameters, you're given preimages of the positive and negative powers. And then the proof will be just a linear combination of these preimages with the coefficient of the witness that you have. Then the verifier can just check that this proof satisfies the natural constraint. And the properties that you require follow the soundness properties follow from the knowledge crisis assumption directly. The prover clearly runs in quasi-linear time, since it performs only 2M additions. And the verifier is polylogarithmic, since it only has to check this satisfying this equation, AU is equal to T sin C. What is actually quite nice is that the language from before also has a proof system from from bulletproof techniques with a succinct verifier. So lattice-based bulletproof is a kind of a set of techniques that allow you to prove knowledge of a SIS, of a witness of a SIS relation using polylogarithmic communication. And the idea is that you reduce to the SIS statement with a half of the dimension, and in each round you send only log many bits. And since there are then you recurse over and over, and you get log many rounds where you in each send log many bits, and overall then you send polylog bits to prove such a knowledge of a witness. And so if you recurse the whole proof system is looks at something as follow, and the bottleneck for this proof system is that the verifier has to run in time linear in the size of the witness that you want to prove. And what we notice is that if M is structured in the sense that it is like a basis commitment matrix, then the verifier can run in time polylogarithmic in the size of the statement. So the idea is that if you have if M is of this form, then when you fold in this bulletproof style technique, you get a statement of the same form times a factor that depends on C1. And then if you recurse over and over, you get you can compress M in a time polylogarithmic in the size of the statement. And with that, I conclude here.
Are there any quick questions from the audience online? Oh, yeah.
Okay, yes. So, yeah, okay. So BCS also achieves polylogarithmic proof size, quasi-linear prover time, and polylogarithmic verifier runtime. They construct a proof system for R-V-SIS, so for all of MP, and the hardness is based on the SIS assumption, so standard assumption, but they get fast verifier through preprocessing. Whereas in our case, the proof system for the knowledge assumption also has preprocessing, but not the one through folding techniques. But there you're only able to prove succinct R-V-SIS. So R-V-SIS statement with some structure where there is a repetition of the same matrix over and over. But that is without preprocessing. So the succinctness of the verifier is straightforward.
So we're over time, so let's take the remaining questions offline and thank the speakers. And we now have a coffee break and we'll resume in half an hour at 10:20.